This is where we're going to start to get really serious about SQL injection. We're going to discover the schema of our internal database application and start extracting data. So this is the real pointy end of SQL injection, the thing that attackers come to applications to exploit. Now there are a number of different ways that we can achieve both these objectives, so let's move on and take a look at the overview and then jump into actually getting data out of the system. There are a couple of real key activities that we're going to cover in this module, and one of them is around actually discovering how the database is put together. So what is that internal structure? What are the tables? What are the columns? What do we need to be looking at as ethical hackers when we want to pull data out of the system? Because that's the real key. We want to actually get the data out. Now, of course, sometimes SQL injection involves inserting data, updating data, running system commands. But evidently, one of the most malicious things that happens in a SQL injection attack is data being taken from the system. And that's what we're going to start to do in this module. And these two things are a little bit chicken and egg. You need to understand the schema in order to know what data you want to pull out of the system, but the process of discovering the schema often involves pulling data out of the system. If that sounds a little bit confusing now, it will all make sense as we progress through this module. Now, the attack that we're going to really start focusing on is the union-based attack, because we want to use this in order to pull the data out of the database via the web application. So we touched on union-based injection in the last module, and this is where, as an attacker, we're appending our own result set with data that's not meant to see the light of day, and we're tacking it onto the legitimate result set. Great way of getting data out, and you'll see just how easy that can be in just a moment. But before we start actually mounting any sort of attacks, it's really important to actually understand how this union operator works. So let's jump back over to SQL Server Management Studio and start by joining up a couple of results using union. So here we are back in SSMS, and I want to demonstrate how union is used. And again, I really strongly recommend when you're trying to craft your SQL injection attacks, jump into a query editor like SSMS or an equivalent for another relational database management system and actually write your queries. Execute them. Make sure that you understand the syntax. And then when you're clear on that, you can start throwing them at a web application via a SQL injection attack. But if you're not sure on the syntax to use, then it's very hard to actually do that. So here's what I want to do. Let's just start by our good old select star from color. And we'll run that, and here is our result. So we've seen this. We know how a select statement now works. What I'll do now is just jump down a couple of lines, and now let's select star from city. Now I'm going to press F5 to run, but I've not highlighted just a single statement. So it's actually going to run both of them. Let's go. So here we can see two result sets. The top one is obviously the colors, and the bottom one is obviously the cities. Let's now take a look at what that union operator does. And we're just going to slot it right in between these two statements. Line returns don't matter, so it can go right here. Now let's run this. So here we now see one result set. So this is a combination of both results. And in fact, if we have a look at these results, we can see that it's interspersed colors, cities, color, city, color, city. And you can see here it's actually ordered by ID, 1s, 2s, 3s. But everything's mixed in together. Now both color and city have a column called name. So we can see that on the right here. But you'll notice that the ID has picked up color ID because that union operator uses the column names from the first select statement. Now, as you'll see in a moment with our case, that will actually work out just fine because the application is expecting the column names of the first select statement. And you'll see what I mean by that in just a moment. One other thing I want to point out here though, this union operator only works because the first select statement and the second select statement have got the same number of columns of the same data type. If we went and changed this second statement, so instead of star we took, let's just say name, and we ran that, you see now we've got a problem. And what it's saying is that all the queries have got to have the same number of columns returned by the result. So what you'll see as we jump into this SQL injection attack is that we've got to make sure that the query that we append in our attack returns the same number of columns as the query that the application is already running. So that's enough of the overview on this union operator, because it is really very simple. Let's now jump over to the sample vulnerable web application and actually start to use this in anger in an injection attack. Back on our sample vulnerable web application, I want to start looking at how we can mount a successful union-based injection attack. So again, how can we take a legitimate set of results already returned by the web application and append a set of results that we instruct the database to give us that the web app normally wouldn't return? And of course, we're going to do that with the union operator. Now, as I just said in the previous clip, the thing that's predicated on making this successful is knowing what columns to return in the second select statement. Because if we don't return the same number of columns as in the existing select statement, so the one returning the results in front of us here, it's not going to work. We'll get an exception. Now, of course, this page, as we now know, is also vulnerable to error-based SQL injection. So if an exception was raised, we'd actually see it here in the browser. And we're going to use that to our advantage in just a moment. So let's try doing this. We're going to jump up here into the address bar again, and right up the end of V12, we're going to close that statement off again. So remember, that'll close the string and allow us to start entering our own SQL syntax afterwards. Now what I want to do is jump straight into this union. So we'll use the union operator, and now we can create our own SQL query. And what I want to try and do is I'm going to select star, and I'm going to select that from, and here is now the point where we've actually got to know what we're going to select it from. So we need to know the name of another internal table that we want to retrieve in the results. Now very shortly, I'm going to show you how to discover that internal schema using SQL injection. But for now, I'm going to make it a little bit easy. In this application, you can vote on these vehicles. And it would be a fair assumption to make that if you can vote on something, there is probably going to be a vote table. So here's the thing with injection, you can guess. And if we get it wrong, again, this does have an error-based injection risk. It will tell us we've got it wrong. But most of the time you'll find that there are underlying entities that are named semantically in line with the entities that you see in the app. So it's very likely there's going to be a vote table. It might be votes, it might be pluralized depending on the convention that the developer followed, but we're just going to go with vote. And of course, as we saw in the previous module, we'll put in a dash dash to simply comment out any SQL that occurs after this is actually concatenated into the SQL statement. And now let's run this. And here we go. We've got an error. So thank you very much, error-based SQL injection. And this error is the same as what we just saw in SSMS when we didn't have the correct number of columns. So the question that we've got to ask ourselves now is how many columns is the original SQL statement returning? Now there are a number of different ways that we can discover this, and I want to show you two right now. And one of them is just simply using a bit of common sense. So let's go back, and I'm going to view the source of this page. So I'm going to do a Control U, brings up our HTML source. I'm going to scroll down a little bit because I want to see where the results for these cars are. And we can see in the HTML markup here, we've got a div, and within this div, we've got the LaFerrari. So we can see the alt tag just here on line 67. Above that, we can see the Pagani Huayra, and below that, we can see the Aston Martin 177. They all follow this same sort of pattern. But here's the thing. I'm interested in what data is being displayed on this page, because that is going to give us a pointer as to what columns might be returned by the underlying query. So I can see really two different data attributes for the supercar. So I can see the name of the supercar here, or the model as it may be, so LaFerrari. And I can also see an ID just here, so ID number 4. So that's two columns. But one of the problems with this as well is that 4 is an integer, LaFerrari is a string, so we don't necessarily know which order they're in, and we also don't know if perhaps the query is actually returning other columns that simply aren't used in the source code here. So let's do this. I'm going to close this tab. We'll go forward again to bring up our query from before, and we can now jump into where that star is in that SQL injection attack in the URL. The %20s either side of that are just URL encoded spaces, so Chrome has effectively taken the space and encoded it for us. Now we can replace that star with what we might guess to be two different columns from the vote table. That's if 2 is right. But there's a really easy way to test this. And the way we can do it is just to type in an integer, and then a comma, and then another integer, and run that. Now this actually tells us something interesting. So we've got a type conversion error here. The specified cast from int32 to string is not valid. So what seems to be happening here is that we've put two integers in the select list here. Now we're unioning this select statement on the end of another select statement. And inevitably that other select statement is returning a string somewhere. And when it gets union with the integer, we get the exception that you see here. So what we can try doing is just changing one of these from an integer to a string. So let's maybe just put a single quote on either side of the second value, just like this. Now this is interesting. And it's interesting because we've now got the Nissan GTR up here, and it's got the number 1 underneath it. Now one of the things that's really handy when looking at the results that a web application is returning is the developer tools in the browser, and in particular the page inspector. So if we right click on this GTR and we inspect the element, we can see here the number 1, and if we have a look in this thumbnail container, we can also see a hyperlink here to Supercar 1, and in there the image with number 1. So what's actually happened is we've got this select statement unioning to the existing select statement and simply selecting one more row with an integer value of 1 and then a string value of 1. And of course that 1 is encapsulated in single quotes that have been URL encoded. So what this is actually telling us is that the existing SQL query on this page is returning a result set that consists of an integer and a string. Now before, when we looked at the source code and we looked at LaFerrari, it would be safe to assume that the integer is the ID of the supercar and the string is the name. So we've now established the pattern. And again, this is a very manual guesswork way around figuring this out. And we'll look at how to extract this information from the database properly as we progress through this module. But let's get back to vote. What we really want to get from vote is columns from the internal vote table. Now it's probably a fair guess that there's going to be a column called vote ID. It's probably either going to be vote ID or ID. So again, these conventions are things that are worthwhile being aware of because we see the common patterns over and over and over again. Now, one of the things I know about the voting mechanism of this website, simply by browsing around it, is that every time you vote, you can also leave a comment. So let's try and do this. I'm going to take out the string number 1 and the integer number 1, and I'm going to try and grab a column called vote ID and a column called comments. Now let's try and run this. And here we now have a very different set of results. And in fact, if we scroll down a bit, we can see we've got all sorts of things here in amongst our supercars. Now here's what's actually happening. we're getting a whole bunch of legitimate supercars. So all the normal ones in the system, that comes back from the original query. But we're then appending all the votes. And for every vote, we're getting a vote ID and we're getting the comments on the vote. So we're seeing things like this. I love the color. That's an existing comment in the system. Is this for real? Another comment in the system. Now the reason why we're seeing a broken image over here is that if we inspect this image, we see down here that it's being referred to as supercar number 19. Now what's actually happening is that we're getting the vote ID number 19, but there is no supercar of number 19. There's less than 19 cars. So consequently there is no image for supercar 19, and we're seeing a broken image. Now that doesn't matter, because what we really want to focus on is the data. So what's important is seeing these internal comments, things like this. That is a comment in that votes table, and we've just managed to spit it back out to the UI simply by appending it with the union operator. Now this is enormously powerful stuff, and so long as we know what the internal table structure is, so we know that there's a vote table that has a vote ID column and a comments column, we can get that data out and put it on this page. Doesn't matter how messy it looks, the point is that we can get the data itself. So how are we going to discover what those internal objects are? The tables, the columns? Well, there's a couple of ways. We guessed what's here in the URL now. Let's move on and start looking at some manual testing to discover what those underlying objects really are. We want to start figuring out what tables and columns we've got in the underlying database of this application. And there are a couple of different ways of doing it. And one way is we can do it in a very manual, somewhat laborious way. We're going to make this much more automatic as we proceed through this module. But I want to start here because it's the most basic, simple to understand one. So here's what I'm going to do. Let's add a little injection attack to the end of this URL. And I'm going to close off this parameter, and then I'm going to put an AND statement. And now what I want to do is say 1 equals, then in brackets, select star from foo. And of course, comment out everything that is left. Now this is a syntactically correct statement. So think back to the previous module when we looked at what the SQL query looked like. We've simply closed off the string that is v12, added an AND clause, and now we've got an equivalency test. So select star from foo must equal 1. Here's the thing though. We're guessing foo, so what's going to happen when we run this statement against a table that probably is not going to exist in the database? Let's find out. We get an exception, but more importantly, we get an exception that is telling us something. Invalid object name foo. The website has just told us that there is no table called foo. This is really valuable, and this is how we use error-based SQL injection to start discovering this underlying schema. Now, of course, foo was always going to be a pretty infeasible table. Let's now change this to something a little bit more likely. Something like user profile. And we'll run that. So now we get a very different sort of error. So the website is no longer telling us that the table doesn't exist. We've got quite a different exception. Only one expression can be specified in the select list. So think about what's happening here. There is actually a table called user profile. We are selecting star from user profile. So we're going to have a collection of columns across a collection of records. And we're trying to see if that is equal to 1, which it never will be. You can't compare a result set with the number 1. You must have one expression in the select list to compare it with the number 1. So now that we know the table exists, we can move on to the columns. So let's change star, and we'll change star this time to bar. And this time we get another confirmation. There is no column called bar. So we're discovering very quickly, by process of elimination, what objects exist in the database. We did that with the table, now we're doing it with the columns. So something more likely to be found in a user profile table is going to be password. Let's do that now. We'll change bar to password, and we'll run that. Okay, different error again. So password does exist, but now we've got a different problem. Now we've got many different rows with one column each. And what the error is telling us is that the subquery, so that's our query in brackets, is returning more than one value. And of course it is, because there are going to be multiple rows. But as we saw earlier on in the course, when we went through some fundamental SQL syntax, it's easy to just get one row. We're just going to get the top one. So we'll do this. Let's now run this one. Now we have something that is genuinely useful. We have this. We have an internal data value. The first password in the user profile table is the word password with a 0 instead of an O. And the reason we're seeing this result here is because SQL Server is trying to compare the word password to the number 1. So that's what's up here in our statement. Now, of course, you can't compare the string password to the integer 1. So you're going to get a conversion failure. And that failure is bubbling up to the user interface because the error handling of the application is not right. It's leaking those internal exceptions. Now, one thing that's worth pointing out here, and I did actually point this out in the last module too, what this exception is showing us is that not only do we have a SQL injection risk in this application, but it is doing a terrible job of storing passwords too. That's a clear text password. That is not a nice strong cryptographic hash of a password as it should be. Now that's a bit tangential, but I did just want to take this opportunity to point out why that is so important, because a risk like this can get access to that underlying storage. So here we are, process of elimination. We've discovered tables that exist, we've discovered columns that exist, and we've actually exfiltrated some data as well. But this was a bit of hard work. We did have to start guessing what things were. And whilst that will usually yield some positive results, it's also all a little bit too much like hard work. So let's move on and have a look at how we can actually query system objects to discover the schema. Let's go check that out now. One of the really neat things about SQL Server, and indeed most database management systems, is that you can query the system itself to discover internal implementation details. So for example, we can run a command such as select star from sys.tables. And when we execute this, we will see all of the system tables, which in this case appears in the far left-hand column. So we already know that we've got a table called color and another called city because we've seen them in previous demos, but there's also one called occupation and another one called president. So there are 4 tables in this system, and this query has just told us this straight away. So we're going to use this query a little bit later on to return all those internal table names out to the web application. Now, one of the other things you'll see here in the result set, now I just mentioned name, which was obviously the name of the table, is object ID. And this is the unique ID of the table. So every one of these underlying objects in the database has its own ID. I'm going to go and copy the color ID because we're going to use this in just a moment. So I'll copy that value. And this time I want to run a different system command. So let's select star from sys.columns. And we'll execute that. And now we've got quite a large number of results. And in fact, if you scroll down through here, you can see just how extensive that really is. Now what we want to do is we want to filter this down because at the moment we're getting all sorts of results from system objects as well as the actual tables that support the application in this database. So let's just jump down a line and we'll add a where clause in here. And we're going to look for that object ID I just showed you. And we'll just paste it in here. Let's now run that. And then here are the columns of our color table: color ID and name. So this has actually been made pretty easy. Sys.tables to get the table names out. The object ID is the individual ID of the table, which we can then use to filter the results from sys.columns to discover all the column names. So now we've got these two simple queries we can run to get all the tables and all the columns. And so long as we can actually get those results back out through the web interface, we can discover the entire internal implementation of this database. So let's jump back to the web app and get this data out via the browser. So we now know that we can use union-based SQL injection to return internal results out via the browser. And we also know that we can use sys.tables and sys.columns to get all the internal object names out of the database. So let's do this. We'll jump up into the URL, we'll close off this string, we'll use a union operator, and we're going to want to get all the data out of the sys.tables system table. So let's do a select, and we already know that we need to select an integer followed by a string. So we'll pick object underscore ID, followed by the column called name, which will be the name of the table, from sys.tables. And then, of course, comment out anything that comes after this statement. Let's now run that. And here are our results. Now we can see amongst all the familiar supercar names, we've got names like make, supercar, user profile, we know of that one now. We know of vote as well. We can also see a few others, things beginning with web pages underscore. There's a few of those. That's part of ASP.NET's default implementation for membership. So we've just been able to extract this data straight out of the system. And that is enormously useful. But of course, as we also know, after that last clip where we looked at the system tables, there is also a system table called sys.columns. So let's imagine that we want to get all of the columns in the user profile table. Now we need to know the user profile object ID. But of course that should be here in the HTML source. So let's right click and we'll go down to inspect element and we'll expand that thumbnail container element we saw earlier. And here's an ID. So let's double click so we can edit this. And I'm just going to copy out that ID, just like so. We'll close those dev tools, and now let's change this query around a little bit. So we're going to want to select from sys.columns. And of course, we don't want every column, we just want the ones where the object ID is equal to what I have on the clipboard at the moment. So now let's drop in a where clause, and of course the where clause is going to consist of where the object underscore ID equals what's on the clipboard. And we'll run that. And now we have a different set of results. And we're seeing things like this. First name. Hey, there's a first name column in the user profile table. There's also a column called isAdmin. Now something like that looks kind of useful because now we might be able to start talking about privilege escalation if we can actually set that to true for our record. We know that there's a column called password already. We discovered that by trial and error a little bit earlier on. And we can see a column called last name, and probably no surprise, a column called user ID. So we've just been able to suck all that data out of the system simply by querying system tables. Earlier on we had to guess, but you don't have to guess when you've got access to sys.tables and sys.columns. Now remember, those system objects will have different names in different relational database management systems. So this is for Microsoft SQL Server. So do consider what is the right syntax for the system that you are testing. Now, of course, everything that we see here is dependent on there being a union-based SQL injection attack vector. And that's not always going to be the case. It may be that you can't inject into the right place for a union operator, And it may also be that where the SQL injection vulnerability exists, there aren't actually any records returned. So what if the injection risk is in an update or an insert statement where it doesn't actually return a result, it just executes the query? For that, we need to fall back to error-based injection. So let's move on and take a look at how we can use error-based injection to get this data out, and that's going to take a little bit more creativity. We now want to try and extract internal schema details by using error-based SQL injection. Now, we already know a couple of things that we could combine together like this. So let's just close off this string, we'll add a clause, and we'll say where 1 equals, and then we'll just add a subquery. Select top 1 name from sys.tables. Comment out the rest, run that, and here we can see the name of our first table, web pages underscore membership. And of course we see it because it's trying to compare that string to the integer up here, that is number 1, and of course it doesn't compare, and that's why we see this data type to int conversion failure. So this is great. We now know that the first table in sys.tables is web pages underscore membership. But what's the second table? How are we going to actually start enumerating through these results? Because the problem with error-based injection is that we can only really get one result at a time. So to start enumerating through the results, let me jump over and show you a quick image that explains what we're going to do. Then we'll jump into SSMS and test out the query, and finally come back to the browser and make sure it works. Let me show you what I mean. Here's what we're going to do. We want to do some enumeration of a database table. And in this case, it's sys.tables. Now what we have to do is just get one result back to the web interface. Because if we get one result, like we saw just now in the browser, we can try and compare that to an integer, let the exception get raised, and then bubble up into the web interface. Now we can get row 1, that's what we just did. But what happens when we want to get, say, row 4? How are we going to get that? Here's what we'll do. We're going to write a query that selects the top 4 records in ascending order. So we'll get row 1, 2, 3, and 4. So that's going to be one result set. Now from that one result set, we're going to select the top 1 result descending. So we're going to go back the other way. We're going to query the results of a query. We're just going to query it in the other direction. Now if we can do that with the top 4, we can also do it with the top 5 and the top 6, and we can enumerate through the records like that. So let's jump over to SSMS and I'll show you what that looks like. So here's what I'm going to do. I'm going to start with a familiar statement, and I'm going to select out of sys.tables, but I only want to take the top 1 result, and you'll see why in a moment. So let's select top 1 name from sys.tables, and we'll order by name. We'll F5, make sure that runs. And now what I want to do is I want to make this a subquery. So I actually want to wrap another query around this. So let's jump back. I'll give it a couple of clear lines for readability there. And now I'm going to wrap another statement around this. And it'll be select top 1 name from, and then bracket, and we'll make that existing query on line 3 the subquery. Then we'll jump down after it, a little bit more room for readability again. We'll close off that subquery, and now we need to alias it. And what I mean by an alias is any string that we can refer to this result set by. We're not actually going to need to reference it anywhere else, but we have to have an alias. So I'll just give it a T for table, and then order by name descending. So we're going to order it back the other way. Now if we run that, we'll get one result. But now let's do this. Let's take this internal query and we'll increment it by 1. So we'll make this number 2 now, and then we'll run again. Now just before I do, See, the result we've got is city. So there's a table called city. Now we'll F5 to run. Now we've got a table called color. Let's change this to the top 3. Now we've got a table called occupation. Top 4. Now we've got a table called president. And if we go to top 5, we're still going to have president because it's still going to be the last result in the list. We know there's only 4 tables in this database. President. 6, still president. 7, still president. So that's how we can easily find all of the tables one at a time. And of course, also easily know when we reach the end of the list of tables. So now that we understand how that works, let's do this. I'm going to jump up and I'm going to put all of this just on one line because it's going to make it much easier to then select it all, copy it, and then take it over to the browser and use it to extract data from our live system. Let's jump over there now. So here we are, same familiar page. We'll use the same attack vector we've used throughout the course so far for error-based injection. So close off the V12 and we'll put an and 1 equals and then brackets to put that entire statement we just pulled out of SSMS in. Close the bracket, double dash to comment anything that occurs after this statement and run. And here we go. Web pages underscore membership. Now if we have a look in the URL, and of course it's all URL encoded now, so it's a little bit harder to read, but we can see that number 7 there, and we can change that to enumerate the results. So let's change it to number 6 and see what table we get. Now here's something odd. So you'll notice that now that I've made this top 6, we're still seeing web pages underscore membership in the exception type. Let's make it top 5 and we'll see what we get. There's the 5. It's still web pages membership. Let's try 4. I can keep going. We'll keep getting the same result. So why can't we enumerate through these records just the same way as we did back in SQL Server? This comes back to the point I keep making about really needing to understand SQL, not just as a query language, but also in terms of the way the target database engine works. Let me show you what I mean back in SSMS. Now this is the statement that we copied earlier on, the one we're having a bit of trouble with in the web app now. And I'm going to do a similar sort of thing here as to what I did in the web app, which is make an invalid cast, just by wrapping a cast around the column name. And in this case, we'll cast as int. And we run this and we get an internal exception here talking about color. Now I was selecting the top 7. Let's try, say, the top 3. We know there's only 4 tables in the database and therefore 4 in the sys.tables table. So we'll run that at 3. We're still seeing color in the exception. Run that as 2. We're still seeing color in the exception. And the problem is related to the way the SQL indexes are built, because the order bys that you see here are actually being processed after the cast because there's no index on this name column. Now that's a real internal SQL Server semantic implementation, but it's one of the things you have to be aware of when you're trying to construct queries like this. Now there is another way that we can do this, and to demonstrate that, I'm going to take a new query window, paste in what I have on my clipboard, and run this again. Now we get president. I'm going to adjust the top results here of my inner query. We'll take that down to 3 like before. Now we've got occupation. Take it down to 2. Now we've got city. And what's actually happening here is instead of trying to select the name and order by the name, we're focusing on the object ID. So it's the same sort of logic in that there is an inner statement which selects from the sys.tables system table. It orders by object ID, and then there's an outer query which also selects the object ID and then orders by descending. And then there's a query outside of that, so this is now a third query, which actually selects the name column from sys.tables where the object ID is the one returned by that query. Now, why is this so messy? Well, by selecting from the object ID and applying that enumeration where we're changing the top number of records and then going backwards and just getting the last one, we can enumerate through and get one ID without any cast exceptions. Now, when we've got that one ID, then we can do what I've got highlighted here, which is to pull the name from the column based on ID, and then we can try casting that name to something that doesn't work. So let me show you what the whole thing looks like, and we'll indent it properly. So there's the second query, and then down here is the third query. And if we nest it back the other way, this is the one on line 4 that's doing the descending ordering. Now I've still got this on my clipboard, so let me go and drop this back into the browser, and we'll see if we can make it work. So we'll jump into where I pasted that old select statement before, down to the end of the URL, paste the query in, and run it. And now we get vote. I'll jump up to the URL, or have to go to the end because this one's a bit bigger, and I'm going to change top 7 to top 6. Now we get make. Let's do one more time, and we'll change top 6 to top 5, and now we will get user profile. So we are actually enumerating through values. I wanted to show it to you this way to make it clear that it isn't really a clear-cut thing. You've got to have that understanding of how SQL Server does things like indexing, and then understand how these tables need to be nested so that they order by the right column to return the right piece of data, which we can then use to cause that internal exception. The other thing I really hope this demonstrates is that SQL Server can get really complex. This is really only scratching the surface, but it demonstrates that there is a depth to it that is often more than initially meets the eye. It also demonstrates how important automation can be, because as things get more complex, yet still adhere to consistent, predictable patterns, automation becomes really valuable. And again, that is something that we're going to look at later on in the course. So that is quite a bit to take on board, but it has shown that we've been able to successfully exploit an error-based SQL injection risk to discover internal schema by enumerating through system tables. So that, in conjunction with the union-based injection that we used earlier on, shows just how powerful injection can be in order to extract really sensitive information out of the database. And of course, we can use exactly the same approach that we just saw here to extract data from the application tables as well. So we just simply apply the same logic that we have here with the name column in sys.tables to the password column in the user profile table. Exactly the same logic. And that should really demonstrate just how powerful this risk can be. Let's summarize the module, and this is the one where things started to get pretty serious. We just wrapped up by showing how easy it is to now pull data out of the system. Now, it actually started off pretty easy with union-based injection, and it makes things a breeze when you can just spit that internal data out into the response and represent it right there in the HTML of the web app. It doesn't get much easier than union-based injection. Now, error-based injection is, of course, still very feasible, and that's something that you want to try and use when that union-based injection isn't available. But it does require you to enumerate through the data. You can't just put one great big result set at the end of another one like with union-based injection. So it does start to get complex. And you need to have this understanding of how the query syntax works and how the database system handles the internal table structure. So we saw that unexpected behavior when we tried to enumerate through records and the cast was being done on the name column before the order by happened. So that starts to get a bit tricky there as well. But of course, all of this can be enormously powerful. And with what we just saw, you now have the ability to not only discover the internal structure of the database right down to every last table and column, but also extract all that data using exactly the same mechanisms that we saw just here. So this starts to get really, really serious. And by now, you should have a good sense of just what a severe risk SQL injection is. But we've still only covered the easiest SQL injection attacks, union and error-based. Let's now move on to the next module and start to look at what it takes to mount blind SQL injection attacks. Now that we've covered off the easy SQL injection attacks, so namely error-based injection and union-based injection, it's time to move on to the hard stuff, and that means looking at blind injection. And as you're going to see in this module, blind injection is all about how we manage to exploit this risk when there is no more low-hanging fruit, no easy error messages, no simple ability to append your result set as an attacker onto the legitimate result set coming back out of the app. So now we're going to start to make things tricky. Let's move on and have a look at what we're going to cover in this module. First up, the main thing I want to establish in this module is when we're actually going to need blind injection. So what are the criteria that make the other easier approaches of error-based and union-based injection unfeasible? And as you'll see, there are a few different things which are going to lead us down the blind path. Now, once we start looking at blind injection, I want to start by looking at Boolean-based injection. And if you recall from earlier on in the course, there are two different types of blind injection. So Boolean being one of them, very simple yes-no sort of scenarios, and the other one being time-based injection. So when we start looking at time-based injection, we're going to use a timing attack, or in other words, we're going to cause the system to take different durations of time depending on different questions we're going to ask it. So effectively, we're going to leak information based on execution time. So that's certainly starting to become a more advanced mechanism of injection. Now, once these two different approaches are understood, we're also going to look at exfiltrating data with blind injection, because it's a lot harder when you can't just simply return it as a union result. You have to actually start to imply things from the way the system behaves, and you have to get very good at asking the right questions by way of the injection payloads that you send to the website. So I hope you enjoy this module. It is going to start to get much more in depth, and these attacks are going to get a lot more sophisticated. So let's go and jump into it. Let's talk by what it was that made these basic attacks successful. And of course, by basic attacks, I'm talking first of all about error-based SQL injection. And one of the things that we saw earlier on in the course is that for error-based injection to work, we need to get SQL errors. So we need to get errors from the underlying relational database management system to bubble up into the browser, because it's those errors that actually contain the useful information. So remember how we did things like tried to compare an integer to a string, and then there was an exception saying that the string could not be cast as an integer, and the string was very kindly returned in the exception. So that makes things really, really easy when the database server is actually telling you what's going on. And all we had to do was just structure the queries in the right way so that the errors contained the right information. So that was error-based. Next up, we looked at union-based injection, and this was really dependent on being able to append our result set as an attacker to the existing result set that the web application was returning. So we had to do things like get the number of columns that the statement returned correct, and also make sure that the data types lined up. But that wasn't hard to do, a bit of trial and error. And what it ultimately meant is that the web interface contained all of the data that we wanted to grab out of the system. So for example, we looked at how we could pull out a list of tables from the sys.tables table. So that allowed us to go through this sort of internal schema discovery process. So union-based injection, very, very easy for pumping results out to the interface. Now again, both these attacks are considered basic in the spectrum of SQL injection attacks. But what happens when neither of these options are available? So what happens when there is no internal error returned to the interface? And what happens when there is no result set that we can just append our own result set onto as an attacker using the union statement? What do we do then? Let's have a look at what the criteria are for making a blind injection attack successful. There's not really a lot required to make a blind injection attack successful. All we need is this. So long as the attacker can manipulate the query that gets executed in the database, it doesn't matter that there's not errors returned to the screen, and it doesn't matter that you can't union one result set to another either. All you need to do is be able to manipulate that underlying query. And what we're going to do in the blind injection attack is infer things based on the nature of the query and the response of the web app. As we progress through this module, you'll see that inference plays a really critical role. So we're going to try and make the web app behave in a certain way that's usually going to give us some insight into a question that we're asking based on the payload we're sending the web app. That'll make more sense as we jump into it. Suffice to say at the moment that we're not going to get crystal clear results like we did earlier on. We're going to have to make some assumptions and particularly make sure that we ask the web app the right questions. To demonstrate where we're going to need blind injection, let's go back to our sample vulnerable app and I'll show you a spot in there where we just simply can't use error-based or union-based injection. And that's the spot that we're going to start probing away with our blind injection. Here we are back on the sample vulnerable application. And earlier on, we were using the cylinder layout page in order to exploit both error-based and union-based injection. So that was one attack vector. I want to show you another attack vector though, and I'm going to go over to the leaderboard this time. And what we'll see on the leaderboard is that the results are sorted. And at the moment, they're sorted by the rank. But we can now expand this little sort results panel, and we can sort by another attribute. So for example, power. And when we sort by power, clearly it's the most powerful cars up the top. Bugatti Veyron rates number 1. What I'm interested in though is the URL. And if we have a look up here, we can see a couple of different parameters. We can see order by equals power in kW for kilowatts. And we can see an ASC equals false. Now it's pretty easy to imply what's going on here. The order by query string is telling us which column to order by, and ASC is the syntax that we'd normally use for ascending versus descending. So give us the power and give us the most powerful supercar first. Now, as we saw when we were looking at error-based injection earlier on, one of the first things we want to do when probing for a SQL injection risk is see how these parameters handle out-of-bound values. So here's what I mean by that. Let's take this power kW value and we'll just change that to say power kW 2. Let's run that. And here we see an error. And in fact, here we also see what we didn't see before, which is an internal error. So this is not an exception from the SQL server that then bubbles up in that yellow screen of death, as they call it, from ASP.NET and tells us everything about the internal exception. What we instead have here is a nice curated error. And really all it says is that something has gone wrong. Doesn't tell us what went wrong. It's a generic error message. Now what's actually happening here is that power kW is actually being concatenated into a SQL query. And because it's an order by clause, we can speculate about where that might be. So for example, it is probably something like select star from supercar, order by, and then we have the column name, power kW, and then inevitably after that we would have the word descending, or abbreviated to DESC, simply because ascending is set to false. Now there are two important things to note about this as they relate to SQL injection. So number one is that if we have injection at the order by clause, that is a very specific place in the statement which happens after other things. So for example, the where clause is done with. We're past that. We can no longer inject into there, and we can no longer apply an approach like a tautology, which we looked at earlier on, because where is done. So we have to find a way of injecting into the order by component of the query. The other thing that this has actually done, and this is really the heart of blind SQL injection, is it has told us something important. It's told us that there is not a column called power KW2. Now that may sound kind of obvious, but it is actually a really, really important concept, because this is the Boolean part of the attack. Ask a question, get a yes or no answer. The question we implicitly asked on the previous screen was, is there a column called power KW? Yes, there is, because the page loaded and it ordered by power KW. The question we're asking here is there a column called power KW2? No, there is not, and consequently we have an error. So that's a very quick understanding of what a blind SQL injection attack entails. Let's now move on and start probing away at Boolean-based injection by using this attack vector that we see right here. We just loaded up the leaderboard page and changed the order by query string value into something which is probably going to be invalid in the database. Now, because there's no error-based injection risk, we got this really friendly error. Well, at least relatively friendly. It's not an internal exception with internal implementation details. So it's telling us that something is wrong. Power KW2 is probably not going to be a legitimate column. Now, what we really want to do in a case like this, before we start probing away at injection risks, is get a bit of a sense of what we think the underlying query might look like. We have to understand what that query looks like, because if we don't get it, then we're not going to know where to inject our attacker's payload. So here's what I'd normally do. I'm going to grab a notepad and pull it over, and I'm going to write out what I would imagine the underlying query looks like. Sometimes this takes a bit of trial and error, but I'm going to speculate as to how I think it's formed. And I reckon it looks like this. Select star from supercar, order by power KW, descending. Descending obviously being what happens when ascending is set to false. And clearly that is the order because we saw the most powerful stuff at the top. Now the most important thing out of all this is that there is a point in the query that we believe that we can inject. And obviously it's this bit just here, this order by column name. And we know that things go wrong when we try to do something like this. So if we can inject at this point, what could we do? Well, how about this? Let's take something that we already know about the internal implementation of the database and see if it works. So this is where we have to play. And I'll just put this on a new line to make it a little bit clearer. So keeping in mind that we do need to have a syntactically valid SQL query, what can we replace this with to start asking questions about the internal implementation? Well, here's an example. What if we were to try select top 1 password from user profile? Now we already know that this is a valid structure. And what I'm looking for is I want to see if we actually get a successful response from the web page or if it fails like what we see here at the moment. So let's copy that out and we'll jump back to the browser and we'll replace power KW2 with that statement. Let's now load this up. So here we go. The page has loaded successfully. It doesn't matter what the actual order is. The important thing is that the underlying query has executed without failure because we no longer have an error message. And again, it doesn't matter that we got a very friendly error message anyway. What that told us was that something was wrong. What this tells us is that nothing is wrong. Let me show you what I mean. If we were to change password to password 2, and there is no column called password 2, let's have a look at what would happen. Here we have an error again. So this is the Boolean-based injection component. We're asking a question. Does this statement execute okay? And we get told either a yes or a no. Now we can keep manipulating that statement and getting yes or no responses. and it's a very binary sort of way of asking the system questions and getting answers. It is, however, also a very laborious way of asking questions. But when we don't have error or union-based injection, this is all we're left with. So we have to start constructing the right questions in order to get the right answers. So with that said, let's move on and start talking about what the right questions are for a Boolean-based injection attack. So we want to actually start extracting some data out of this page that's at risk of a blind SQL injection attack. And how we do this is all going to come down to the sorts of questions we can ask. So just before, we found that if we sorted the results and we went to power, we had this reference to a power KW column. Now when we did this, we had the Bugatti Veyron in position number 1. Now if we sort by top speed, we can see that now the order by clause is top speed KM, and we've now got the Koenigsegg in position number 1. So depending on whether we order by power KW or top speed KM, we'll get a different result on this page. Now that's really a Boolean condition insofar as if we can ask a question and then say, hey, order by power KW if the answer is yes, but then order by top speed KM if the answer is no. If we can do that, now we've got ourselves a valid way of asking good questions. So let's jump back to our notepad and see if we can construct the right SQL query to ask that question. And this is where it really comes back to your knowledge of SQL again. Now, one question that we can ask at this point, and remember, it's very, very context specific. We have to use the right syntax in the right place. So how we'd inject into a where clause with a blind injection attack is very different to how we need to inject into this order by statement. Now, one pattern we can use here is we can use a case. And basically what case says is case when something, then use this column, else use that column, end. So the case when, then, else, end syntax that we can use in order by will allow us to ask a question and then get a different answer based on the result. So let's do this. Let's use this when condition to find out the number of tables in the sys.tables system table. And what I actually want to check here is when the number of tables is equal to 10. So let's do this. Select count star from sys.tables equals 10. So pretty self-explanatory. The syntax is the main thing to get right. Obviously, we're going to say this condition will simply be true when there are 10 tables. And if it is true, I want to order by power KW. Now, if it is false, then what I want to do is order by top speed KM. So depending on the resulting order of this page, we're going to be told whether there are 10 tables in the database or not. Let's copy that onto the clipboard, over here into the browser, and we're going to replace this existing parameter here with what's on the clipboard. Let's give that a go. So here we can see the Koenigsegg has come up in the first position. Now the Koenigsegg was our else result for the question of whether or not there were 10 tables in sys.tables. Now clearly there are not 10 tables because we're seeing the Koenigsegg. But what if we did this? What if we asked, are there less than 10 tables? So we tried it this way. Now the Bugatti Veyron's at the top. So the answer is yes, there are less than 10 tables. And all we have to do now is just narrow down the query. So let's ask if there are more than 5 tables. Bugatti's still at the top, so yes, there are more than 5 tables. Let's see if there are less than 8 tables. No, there are not less than 8 tables. We've got the Koenigsegg at the top. So we're narrowing down this range of different possible results. Let's ask very explicitly now, are there 8 tables? So we'll make that an equals. Run that, and the Bugatti is at the top. So the answer is yes, there are 8 tables in sys.tables. Now by taking this approach, by starting to use less than or greater than, we can greatly reduce the number of requests we have to make because now we're asking about a range of different possible answers instead of asking about one very specific result. Now, when you ask about ranges, you can start halving those ranges with each subsequent question. So for example, you could ask, is it less than 12? Yes, it is. Is it greater than 6? So we've gone halfway. Yes, it is. Is it less than 9? So you see how you keep splitting the difference in order to minimize the number of requests that need to be made. But that was really the easy bit. That's just a numeric question. What happens when we want to get specific and we actually want to know letters? So for example, what happens if we want to know the name of the first table in sys.tables? Well, now we've got to start asking a very different question. We could ask this question very specifically. So for example, we'll go back to Notepad. We could ask if the top one name is equal to foo. So that would be a yes or no question. Let's try that. We'll copy that onto the clipboard. We'll paste it back into this order by clause here, all the way through until the and ascending query string parameter, and we'll run that. Now it runs, there's no error, so our syntax is right, but we get the Koenigsegg. So the answer is no. The first table in sys.tables is not called foo. And remember, at least for Microsoft SQL Server, the default collations are usually not case sensitive. So it's not foo all lowercase, and it's not foo with any other combination of cases. But the chances are it was never going to be foo. And although we could guess at some table names and probably get a hit every now and then, this is not really a way of enumerating through and getting an accurate list of all the tables. We have to stop asking such specific questions and ask a more generic question. And the question I want to ask is, what is the first letter of the table? There are still obviously 26 possibilities there, but let's just ask that question. So I'm going to jump back to Notepad again, and let's now change this query. So here's what we'll do now. Rather than selecting the entire top one name, we're going to get just the first letter of name. So that's going to require us to do a substring. And it looks just like this. Substring, and then the parameters of the substring method take the name first, the start character, and then the number of characters you'd like to take from that start character. And in this case, it's just going to be 1. So this pattern will give us the first character only of the name column. And then of course, rather than comparing it to foo, we'll just compare it to A. So obviously first letter of the alphabet. Now this is going to be somewhat laborious, but in a moment we'll see how to expedite this process. Let's just start here. So again, we'll replace what we've already got there, paste it in, load it up, and it's still the Koenigsegg in number 1 position. So the first letter of the first table in sys.tables is not an A. Now we could keep going, but clearly this is going to be really, really laborious if we have to keep guessing every single letter. And that's just the first letter of the first table too. Inevitably there are going to be a lot more letters to guess. But there's a smarter way of doing this, and that's enumerating via ASCII values. So let's go and take a look at what I mean by that. What we need to remember with this kind of SQL injection attack, a blind attack, is that we are just asking questions, and we're really just asking yes or no questions. Now earlier on, you saw me trying to discover how many records are in the sys.tables system table. And I started out by trying to guess explicitly, is it 10? And then I said, well look, what we can actually do is we can ask about a range. So we can say, is it less than 10? Is it greater than 5? And we can really slash the time that it takes in order to make the guess. Now we can do exactly the same thing with letters as well. We just have to convert the letter to a number. And the easiest way to do that is to take the ASCII value of the letter. So what you're looking at here is just a standard ASCII table for lowercase letters. Now of course, you could still have tables that have non-alpha characters in them. Could be numbers, could be a small subset of symbols. So we're simplifying here. and you may need to expand your scope beyond just these 26 ASCII values. But that's pretty straightforward to do, so long as you know the ASCII ranges that you're looking for. Now I want to show you how we're going to ask questions about this ASCII range. Main thing I want to point out now is that M is the 13th letter of the alphabet. It's dead center. And M is ASCII character 109. So let's have a look at how we're going to ask the questions of the database via a little decision tree. It becomes much easier to discover a letter in a position once you start asking the right question related to ASCII range. So for example, the first question I want to ask is the ASCII value of the first character less than or equal to an M? Now if it's no, then I'm going to go right, and I'm going to ask about S, because S is the next middle character between M and Z. Now if that's a no, we're going to fall down to, is it less than or equal to V? So now we're narrowing down this range. We're somewhere greater than S, but less than or equal to V. Now we might get a yes response this time. So now we split again. Is it less than or equal to T? And obviously greater than S. No, it's not. Therefore, it's got to either be a U or a V. That's all we're left with. So we can ask that question explicitly because it's the last possible option. And then we're either going to get a yes or a no. So even though we've got 26 letters in the alphabet, you can see that this was just 5 questions. So let's go and give this a go and see if we can discover the first letter of the first table in our sys.tables system table in only 5 questions. So let's go and build up this query. I'm going to jump back into Notepad. We are going to need a little bit more room for this one because we're going to have to run a couple of other functions here. So what we have already is we do have the substring, so we've got the first character of the name. What I want to do first is I want to lowercase that, because if we're comparing to the ASCII range, even though this collation on the database may not be case sensitive, we're still going to get a different ASCII value for lowercase versus uppercase characters that are otherwise the same. So I'm just going to wrap a lower around this, and we'll close that off at the end of the substring method. So that's the first thing. Now we're going lowercase. The next thing is to get the ASCII value. So I'll wrap another function around this, and it is just ASCII. And then we'll close that guy off as well. So that's all we need to get the ASCII value. Then of course what we're going to be doing is looking for ranges. And the first thing we're going to do is less than or equal to the letter M. And of course M was ASCII character 109. So I'm going to copy this line and I'm going to jump back over to the website. And let's now drop this into our query string. So that'll be everything from the starter case up until when that ascending parameter starts. And we'll paste it in. And of course keep in mind the question we're asking here is whether or not the first character of the first table name in sys.tables is less than or equal to an M. Let's run that. And we get the Koenigsegg. So the answer is no. So we have to change our question. Now what I'm going to do is let me just reposition this window partially over our ASCII table from before, because I want to figure out what letter to do next. So if we want to go halfway between M and Z, we're going to want to take about an S, which is character 115. So let's now change this value, and we'll jump into the right spot here, 109 to 115. Run that. We've got Koenigsegg, so the answer is no. The first letter is not less than or equal to S. So we split again. Between S and Z, we'll go to about V, character 118. So let's see where we stand with 118. Still no. We've still got Koenigsegg. So it's greater than a V. We can figure the rest out just in our head because we're only down to a few letters now. So let's jump up a couple from V and we'll go X. So that'll be 2 more numbers. So 120. And now we've got Veyron. So now we know that it's not less than or equal to V, but it is less than or equal to X. So it must be either W or X. So now we can actually ask an explicit question and we can get an absolute answer. And the explicit question I want to ask is it equal to W, which is 119? Load the page, and there is the Bugatti. So the first letter of the first table in sys.tables is a W. And this is blind SQL injection now actually telling us something really specific. So something we can actually use. We know it's a W, we can keep enumerating through. So we can change it from substring 11 to substring 21. So start in position 2 and take one character. Is that equal to a W? Well, it's the Koenigsegg again, and we could repeat the whole thing, but clearly you now know what the process is. You can go through this process to discover all the tables and their names, all their object IDs in sys.tables, which you can then use to start enumerating through sys.columns and find all of those names. Now, what I will point out is that I did greatly simplify it here. I kept it to simply letters. Keep in mind that object names may have numbers and may have a limited set of symbols. So for example, an underscore. So make sure that as you're asking these yes and no questions, you're asking the right questions and you're not excluding characters which could actually exist in the underlying database names. Now, the last thing I'll say on this mechanism of SQL injection is that yes, it's laborious. In fact, it's very, very highly laborious. And it is the sort of thing that is a repeatable pattern. We could manually go and just keep moving one position at a time and asking those 5 questions about the character, or we could automate it. And inevitably, a blind SQL injection attack is going to be something that's very heavily automated. We will look at automation tools later on in this course. But it's really important that you understand the underlying mechanics, because without knowing how this actually works, your ability to exploit especially increasingly complex SQL injection risks will be rather limited. Now, with that said, that's Boolean-based injection wrapped up. Let's move on and start looking at time-based injection as well. Now that we've got a good understanding of Boolean-based blind SQL injection, let's move on and start looking at time-based injection. And this is where things start to get a little bit trickier. So I want to give you an example of where we might use a time-based injection attack. I'm back on the Supercar Showdown site. I'm going to scroll over a couple of vehicles until I get to one I haven't voted on. So the Pagani will do. We're going to have a look at the Pagani. Now we can see a vote button here on the left. So let's click on that. And I'm going to leave a comment here, and we'll just leave a comment of nice. And we'll vote. Now here's the thing. I don't get any data at all in the response from this request. The thank you for voting that you see on the screen here is simply displayed when the HTTP response status indicates the request has been made successfully. So because I don't get any direct UI feedback, I can't use, say, a union-based SQL injection attack where I actually append a result set to whatever was generated by the app. And it's also going to make it very hard to use a Boolean-based blind injection attack because I can't change the body of the response. And as we'll see in a moment, there is no response body. About the only option left would be an error-based SQL injection attack. And of course, we'd need to depend on the application actually exposing internal exceptions or giving us another indication that there had been an internal error. But you don't always have those options, which brings us to a time-based blind injection attack. So we're going to assume that yes, there is an injection risk, but all we can do is get our arbitrary script to execute on the server without actually seeing a change in the response. So to demonstrate how we're going to do this, I want to start by going back to SSMS and having a look at a bit of SQL syntax. To properly understand a time-based attack, I want to start by showing you a little bit of syntax. And here's what I'm going to do. Let's begin by running a simple select sysDateTime. So this will just run that function, and if we execute it, we get the current time on the machine. I'm going to wrap a little go statement after that, and then we're going to run another statement after that. And the statement we're going to run here is really the crux of a time-based blind injection attack. So here's the command I'm after. Wait for, delay, and then a time period comprised of hours, minutes, and seconds. So we're going to give it 5 seconds. So there's our delay, and then we'll run another select sysdate time. And this will give us the time after the delay. So let's now run this and see what happens. There's one response immediately, but the bottom left says executing query, so it's still running. There's the second response. And we can see quite clearly that the first result says 11:35 and 9 seconds in the AM. The second result is 11:35 and 14 seconds. There's a fractional difference in the actual milliseconds whilst SQL moves on and processes the next statement, but for all intents and purposes, these two results are 5 seconds apart. Now this is actually very important because what it means for a time-based blind SQL injection attack is that if we can inject that wait for delay command anywhere into a SQL statement and we can observe that time delay in the web app, then we can start asking these Boolean questions again. Except rather than say ordering the results by a different column, we're just telling the system to either respond immediately or take another 5 seconds to respond. And so long as we can measure that time, we can then get the answer to the question, just like we did back in Boolean-based injection. So let's jump back over to the web app and actually start constructing a time-based attack. So here's what I want to do in terms of how we construct this time-based blind SQL injection attack. First thing is, I want to go and find another vehicle I can vote on, because once I've voted on one, I can't vote again. So we'll go back to the leaderboard, and I'll jump down to, say, the Mercedes-Benz. Let's go there. Okay, so now we can go into vote again. Now, ultimately, what we're going to want to do here is manipulate this query. And it's very hard to manipulate a query like this in the browser. So this is actually an asynchronous post request. So what I want to do is actually capture that request when the vote is made, and then we'll manipulate that request and reissue it. Now the way I'm going to do that is with Telerik's Fiddler. So let me jump over there now. So here we are in Fiddler. And really, you could use any tool at all that allows you to reconstruct HTTP requests. The reason I'm using Fiddler is that it's very easy to capture the request, manipulate it in the composer, and then reissue it. And if Fiddler is something that's new to you, go and check out my Hack Yourself First course, where I give a pretty good intro to it in terms of what it does in scenarios like this. So Fiddler is now running. It's going to capture the request that we make when we vote for that Mercedes-Benz. So let's jump back over to the browser. And in fact, I'll even just snap the browser over to the right-hand side of the screen so we can see the request in the background. Now this time we'll keep it simple. I'll just put in a comment called foo. Let's now issue that vote. And in the background, we can see the request. Now a couple of things to note here in this request. So first of all, if we look at the request headers over to the right, you can see that it is posting to /API/vote. I've mentioned multiple times throughout this course that the HTTP verb has no consequence on the vulnerability to SQL injection. So whether it's get or post, or even something like delete or put, the same vulnerability exists. The big difference with things that are not a GET request though, is it makes it a little bit harder to just reconstruct in the browser. Regardless, it's easy when you can construct the request in a tool like Fiddler. Now the other thing we'll look at is if I go down and look at the response, and I look at the raw response, there is no response body. All we're seeing here is response headers. So this goes to the point earlier on, where it's trickier to use something like a union-based injection, or even a blind Boolean injection, when there's no actual response body to look at. Now one option here would be to explore an error-based injection, or another vector which changes the response code of this particular request. But what we're going to do here is use that blind time-based injection attack. So let's do this. I'm going to jump on over to the composer, and I'm going to drag this request over to there now. And what I want to do is inject in down the bottom just here. So we can see here in the request body, our comments equals foo. Let's go and grab Notepad and the query that we constructed a little bit earlier on in the Boolean-based injection. So here it is, and that worked well in the context of the order by clause. So this is when we used a case statement to either order by power kW if true, otherwise top speed km if false. We can't order anymore in this particular attack. But what we can always do is close off the existing SQL statement and then inject our wait for delay clause. So the first thing we've got to do when looking at this statement is figuring out what's the right syntax in order to drop this in after foo in the comments. Now inevitably we're voting here. So we're actually going to be creating a record. This is going to be doing an insert into a table. And as we saw earlier on in the course when we looked at those SQL syntax fundamentals, this is inevitably going to adhere to a syntax such as insert into table name, followed by column names, and then values. And the values is a comma delimited array inside a set of brackets. So here's what I'm going to do. Let's just take a new line up here, and let's imagine what happens after foo. I'm going to close off the foo string, I'm going to close off the bracket at the end of values, and then I'm going to terminate the statement. So this should now give us some clean air to write our injection attack. Now this time I'm going to use an if statement, and it's simply going to look like this. We're going to write if, and then the condition, which will be everything in brackets over here, the equivalency, which will be the less than or equal to 109, and then I'm going to take out the remainder of that old case statement. So that'll be everything from the end all the way through to the then clause. So here is where I want to put my wait for delay. And just like before, we will give it a delay of 5 seconds. And then just to make sure that any remaining syntax that would have appeared after foo in the request body below doesn't actually get executed and inevitably cause a failure because it wouldn't be syntactically valid, we'll use the old comment syntax, just like that. So recapping, this line here should close off the insert statement, check to see whether the first character of the first record in the name column of sys.tables is less than or equal to m, and if it is, it's going to wait for 5 seconds. If it's not, it's going to respond immediately. So let's copy that onto the clipboard, and we'll now drop that down into the composer right here. And we can now just execute this request. Now that responded pretty quickly. So let's check for the inverse. Let's go down here and change less than or equals to greater than. And we'll execute that. Now it's waiting. This hasn't responded immediately. We can see a delay. And there is the response. So the time-based injection attack has just given us two very different answers, depending on whether we're looking for a letter less than or equal to m or greater than m. Now we know from the earlier attack that we did using Boolean-based blind injection that the first letter of the first table in sys.tables is actually a W. So this reconciles with that other test. Now just to be sure about durations, let's go and click the first request we did over here. We'll look at statistics, and here we can see an overall elapsed time of 0.76 seconds. We look at the second request, and here's an overall elapsed time of 5.29 seconds. Now one thing about a time-based SQL injection attack is figuring out what is the right wait for delay duration, because 5 seconds is quite long. And in reality, we could probably get away with only about 1 second. It would certainly allow us to mount the attack at a much faster rate rather than waiting an extra 5 seconds every time we got a true result. But of course, the trick here is not getting false positives, because the very nature of the internet is that sometimes we're going to have randomness in our response times. So you wouldn't want to have such a small value that you're not sure whether you actually got a true or a false answer, but you don't want to have such a large value that it's going to take a long time. The right figure is something you can establish by ascertaining how reliable the connection is. So issue a bunch of requests, what sort of range are the response times, and then making sure the wait for delay period is sufficiently large that you'll always be able to know when it's that condition that's been hit. Now again, as I said when we talked about Boolean-based blind SQL injection, this is laborious and it's repetitive. In fact, it's even more laborious because you've got to wait for these durations. And it's exactly the sort of thing that benefits greatly from automation. And as I've said multiple times throughout the course, we are going to look at automation later on. But this was important for you to understand the underlying mechanics of how a time-based blind injection works. Let's summarize the module. And this was where our SQL injection did start to get a lot more advanced. And really, the place for blind injection is where we can't get useful data out of the response. So we can't get explicit internal names based on a SQL exception. Or we can't just append our result set to the result set the app was expecting using a union-based injection. This is where blind injection really comes into its own. And the crux of blind injection is asking questions. Is this condition true? If yes, then go and do one thing. If no, then go and do another thing. And using ASCII character ranges makes this significantly easier because you can just continually chop your possible range of answers in half. It's still laborious, but it's a lot faster than checking the equivalency of a specific character. So ASCII ranges, very important. Now, of those blind injection attacks we just saw, we could go down the Boolean path, where we can actually manipulate the response. So we change the order of the supercars based on whether our question was true or false. And of course, when you can't actually manipulate the response body in a way that you can observe, you go time-based, and you create another observable response, which is duration. Of course, that can be very time-consuming, but again, automation through smart tools can work around those human limitations. So that's blind SQL injection, both with Boolean and time-based. Now that we understand that, let's move on to the next module and start to look at some really advanced SQL injection concepts. Now that we've covered off the fundamentals of SQL injection attacks, so everything from error-based injection, union-based injection, and then most recently through to blind-based SQL injection, both Boolean and time-based, it's time to move on to some of the more advanced concepts. And as you'll see during this module, there's a whole lot more to SQL injection than what we've seen so far throughout this course, both in terms of some of the semantics and idiosyncrasies of injection, through to some of the more powerful things we can do with it once we can start running arbitrary commands on a target. So let's move on and have a look at what we're going to cover in this module. This module is really going to start to go beyond the fundamentals that we've seen so far throughout this course. And one really important thing we're going to kick off with is understanding how there are different syntax semantics in relational database management systems. The attack that we mount on a system using Microsoft SQL Server is going to be different to one that we use on a system that's using MySQL. And I'll give you a really simple example of that in just a moment, as well as showing you where you can find much more detailed information. We're also going to have a look at how we can discover the access rights of a user, as well as the other databases on the server that this system is using. Because this is going to give us a lot more power, knowing what we can do and what other databases we can do it on. Why just constrain ourselves to the one database? Let's go and expand our horizons. Now, further to that, we're also going to look at how we can create other ways of getting into the database. So SQL injection might be the entry point, but we'll look at creating a login so that you can come back and just jump straight into the database. Let's take the web app out of it. We'll give ourselves a back door into the system via a new login. And finally, we're really going to go beyond just interacting with data. SQL injection is extremely powerful because we can execute things on the target server, not just on the target database, but on the operating system that database server is running. That's going to give us some really powerful options. So that'll be quite different to the attacks that you've seen so far throughout this course. So with that said, let's move on and start having a look at how the SQL syntax can differ across database implementations. At multiple times throughout this course, I've reminded you that the syntax we've been using is for Microsoft SQL Server, and it can differ for other relational database management systems. So I want to give you a really basic example of what I mean by that. Let's take two database servers. So SQL Server, being the one that you're probably most familiar with after this course, and MySQL, another enormously popular database server. Now let's take an example. In SQL Server, if we want to grab the top 5 records from the widget table, we would run this query. Pretty straightforward. We've seen that already in this course. However, in MySQL, it'd look like this. So only a very minor difference. Instead of a top 5, we've got a limit of 5, but obviously also in a different position in the query. Now this is really important because they won't interchange. We can't run a top 5 star against MySQL, and we can't run a limit 5 against SQL Server. So establishing what the database server is a really critical step to mounting your attacks, because you've got to make sure you're running the right syntax. We'll have a look at how to discover that in just a moment. Now this is just one very simple example, but I want to show you a more comprehensive list of differences. Firstly, so that you appreciate just how much variance there is between database servers, and secondly, so that you've got a good resource to go to when you need to figure out how to construct your attack. Let's take a look at that now. There are plenty of resources on the web that explain the language differences between different database servers. The reason I'm showing you this one is because I like how comprehensive it is, and it gives you some great examples. So as I page down through this list, you'll start to get a sense of just how complex this topic can be. And in fact, what I want to do is just page down to one example, and it's this one, inserting several rows at a time. And what you'll see as we scroll down a little bit further is a good example of the variances I'm talking about. So let's take this syntax just here. Now you could take this syntax and you could use it against Microsoft SQL Server, but only if it's SQL Server 2008 or newer. You could use it against MySQL, and that's fine, you'd get away with that. But then you couldn't use it against Oracle because, as they say here, there is an Oracle-specific kludge of this implementation. Now that's just one very simple example, and you can get a bit of a sense by how much stuff there is on this page just by virtue of the fact that we've only scrolled about a quarter of the way through it. Now the thing with this here is it shows us that not only are there differences between database management systems, but there's also differences between versions. So that SQL one is a perfect example. If you're using SQL 08 or newer, you can use the syntax. If it's earlier, and there is still a lot of stuff out there that's earlier, then it simply won't work. As we progress through this module, you'll also see some semantics about the SQL implementation on our sample vulnerable website. That's running in Microsoft's Azure SQL database implementation. And that has its own semantics as compared to the full-blown SQL Server instance that you'd run on, say, an on-premise installation. So again, understanding the versions is really important. So let's jump over to our sample vulnerable site and I'll show you how to find the version of the underlying database. So back on our sample site again, let's jump back down to those engine capacities. We'll grab the V12s again, and we know that we can inject using error-based injection right at the end of this query. So let's do this. We'll close off the V12, and I'll add a statement here. And 1 equals at version, and we'll comment out everything after that. So let's run this and see what we get. Now, as we know already, that equivalency with the number 1 is going to cause a typecast exception. And consequently, the error-based SQL injection risk on this page has returned the internal database version. And it's everything from here down to here. even including line returns. So we can see here that it is running on Microsoft SQL Azure 12 point something. And in fact, this version was updated on April 15 of 2015. So we now have some very, very specific information about what this version is. Now that we know that, we can tailor our attack and make sure that we're actually using SQL Server syntax and not Oracle syntax or MySQL syntax. Now, having said that, whilst this discovery is important, you can often make pretty educated guesses about the underlying database system. So if you're looking at Microsoft technology, so for example ASP.NET, and you can tell that via either response headers, page structure, or even file extensions, there's a high probability it's going to be running on Microsoft SQL Server. If you're looking at the LAMP stack, so for example PHP running on Apache, and again you can tell this from response headers and page structure and other common telltale signs, you're probably going to be running on MySQL. So even when that internal version isn't immediately discoverable in this way, you can usually make a pretty educated guess. A notable exception that has been emerging in recent years though, is the rise of NoSQL databases, CouchDB, MongoDB, RavenDB, and other data constructs such as Microsoft Azure's table storage. There are many more implementations today that aren't queried using SQL syntax than what there were just a few short years ago. So just be conscious that even if you are looking at a data-driven website, that doesn't necessarily mean there's a database underneath that may be exploitable via SQL injection. So keep that in mind as well. With that said, let's now move on and start to have a look at how we can discover more information about the internal implementation of the system. One of the things you want to do in an injection attack is ascertain what account the web application is using to connect to the database, and then more specifically, what rights that application has. So is it just going to let us read data out of the system, or can we write it? Or can we drop and create objects? The rights of this database account is absolutely pivotal to how successful you can be in your attack. Now we're going to look at a couple of different things here. And the first one I want to look at is just getting the identity of the current user. So here's what we're going to do. We'll close off V12 again, and this time we'll make our equivalency test equal to current_user. And let's run that. So now we get the username that the web app is connecting to the database with. It's called Hack Yourself First Restricted. Now this particular name is not necessarily going to tell you a lot. In fact, I've created this account so that it has enough rights to demonstrate SQL injection attacks, but not enough rights to completely destroy the database. Hence why I named it restricted. What you will often see though is accounts like SA, server admin, that has God rights over the entire database. And all too often you see developers making web apps connect to the database with this account, because it sure makes permissions easy when the web app can do everything. Nothing is restricted. But of course that is a terrible security decision, and you can often disclose that shortcoming just by looking at the current user. Regardless of what the name of the user itself discloses, we can start looking at what rights the user has. So let's try this. I'm going to change the current user test here to select is_role member, and then I'm going to pass the name of a role that I want to test for. And I'm going to start easy. Let's start with DB Data Reader, which is a SQL Server role which grants data reader rights. And by default, it'll grant data reader rights to every table in the database. Now this function, is_role member, will either return true or false. In fact, it returns a 1 or a 0. And that's going to give us a slightly different response to what we're used to. Let's run this. Now here's the thing. We've actually got vehicles in the result. So this is not an internal exception. And it's not an internal exception because this has returned a 1. 1 can be tested as being equal to 1 because remember this is our equivalency test. 1 equals. But really what we've got ourselves here is a Boolean-based blind injection attack. because the page has loaded. So remember, what we're testing for here is and 1 equals and then some value. So if it is equal to 1, we're going to get results. So from this, we can surmise that yes, this query just here, select is roll member, db underscore data reader, is true. So the user the web app is connecting with is a member of the data reader role. Let's check for data writer. Also results. So the user is also a member of db underscore data writer. So now we know that this account, again, by default, unless it's been explicitly overridden on one of the actual database tables or columns, has the ability to write to everything. So that's useful information. Let's go one step further and check for DB owner. And now we have no results. So this query must have returned a 0. The identity the web app is connecting to the database under is not a member of DB owner. So what that tells us is that we won't be able to create objects, we won't be able to drop objects. And again, I've had to do that in this system so that I can keep it public for you to use it without someone coming by and just absolutely destroying everything. So that's good, but what it has told us is that anyone that can come by this web application can read and write from everything, and that is way too excessive. And later on in this course, when we talk about SQL injection mitigations, we're going to talk about the principle of least privilege and how you can restrict the access rights the web application has when it connects to the database server. But of course, this is a sample vulnerable application, and it is meant to show these bad practices. So that's establishing account identity and rights. Let's now move on and see how we can start to find other databases on the same system. In the last clip, I just explained how the live production system of hackyourselffirst.troyhunt.com does have somewhat limited rights. I have to do that to keep the thing alive. But I do have a local version running on my machine, and it's got this local prefix you see here. Now this local version has the web app connecting to the database with God rights. It can do anything. And because of that, I can show you a few behaviors that you can't see on my public site. Unfortunately, you can see it on many other people's public sites. This is why SQL injection remains in that #1 spot. But here's what I want to do. Let's scroll down and we'll look at the V12s on my local system, and we'll use the same attack vector as we have on the live site. Now what I want to do this time is I'm going to use a union-based injection attack, and I'm going to union the results of this page with select 0, because remember, we know this page returns an integer ID followed by a string, so 0 will satisfy the requirement to have the same number of columns of the same data type, and then I'm going to select the name column from sys databases. Let's run that. And here are our internal database names. So things like 01 injection. And in fact, this is a database used in my OWASP Top 10 for ASP.NET Developers course. All of these ones you see here are from that course. They've shown up first simply by virtue of having been sorted alphabetically. The real point here though is that this sys databases table is showing us all the other databases on the system. So no longer are we just constrained to looking at the Hack Yourself First database. Now we're seeing the other databases. But of course, we're only just getting started. This is just database names. So let's take something like that 01-injection database and find out what tables are in there. So I'm going to want to select out of sys.tables. And we know that in sys.tables, there is a column called name. So I can actually leave my select statement here the same. All I'm going to do is I'm going to change the database I'm selecting from. So let's change it to 01-injection, and I've put this in square braces because once we have a dash in an object name in SQL Server, we need to encapsulate the name in braces, and then .sys.tables. So this is just fully qualifying the database name that the table exists in. It means that we can run this query from any database and get the results for the target one. Let's run that now. and it doesn't work. We have ourselves a different problem. And I want to show you this problem just to demonstrate the sort of idiosyncrasies that you can come across when running this style of attack. Now this is a collation conflict. And what it's saying is that the collation of the name column in sys.tables in that injection database is not the same as the collation of the column which is being returned by the query on this page. So that'd be the one that's actually returning supercars with model names. Now this is all happening because you can't compare two different collations or union them together, or else you'll get this exception. But we can work around this very easily. We've just got to cast the new column as the target collation. So let's just copy the name of this collation onto the clipboard, and then after the name column up here, which is where we're having a collation issue, we'll just collate, paste, and run. Problem solved. Now we can see our table names. We've got a table called credit card, which looks particularly enticing. We've got product, product category, product subcategory. So we've managed to get all of these table names out of the other database. Now from here, we can go on and mount all the sorts of attacks that you've seen already throughout this course. So long as the web application that we're connecting to the database with has the rights to query these other databases, we can get all the data out. It's exactly the same attacks as we've seen earlier. And what this is really demonstrating here is the problem with excessive permissions on the database account the web app is using. There is no reason why the account that this app is connecting to the database with should be able to read data from every single database on the system. And again, we'll talk about the principle of least permission later on in this course. But the unfortunate reality is that a lot of web apps are connecting with either God rights or accounts that have way too many access rights across way too many databases. And that means that you can do stuff like this. But it can be even worse. Let's move on now and have a look at how we can actually create new database logins. So far in this course, all of our SQL injection attacks have relied on exfiltrating data via the web app. Now sometimes that's been quite easy, such as with the union-based attacks. But as you would have seen in the blind-based attacks in the previous module, it can get really laborious trying to suck this data out through the web app. So rather than have to do everything over HTTP through the website, let's actually just create a new login in the database. Now I'm back on my local version of Hack Yourself First here, because you simply can't do that in the Azure one. And in fact, Microsoft's Azure SQL database model won't even let you create logins unless you can execute in the context of the master database. And the web app isn't connecting to that one. So Azure actually has a pretty good neat native defense there. In my local one though, there is no such defense. So let's do this. We're going to manipulate this query string again. And this time, I just want to close off the statement outright. Now, let's actually create a new login. So here's the SQL syntax. We're going to run create login, and we'll just call it my login, with password, and we'll give it a very simple bad password. Let's run that. Now the page is loaded without error, which means that we just created a syntactically correct query which we tacked on the end of that v12 condition. So in theory, this should have created the login in the database. Now a login is one thing, but actually having the permissions to do much is another. So let's now do this. Let's add it to the sysadmin role. And the way we're going to do that is to run the command alter server role sysadmin add member my login. Let's give that a go. Okay, so that also executed successfully. So now we should know both the login and the password in order to remotely connect to this machine. But there's one other thing that we need to know first. We need to actually know the name of the server. So now let's go and grab that as well. And we're going to go back to this equivalency test in order to cause an error-based injection. So it's going to look like this. And 1 equals at server name. And here's our machine name. And this one is just Troy PC. So that's everything we need. Now what I will point out is that this is the internal machine name. That's usually not going to be externally accessible via that name without being part of a fully qualified DNS name. Even then, it may still not be externally accessible unless you have the IP address, and I'm going to show you how to find that later on in this module. So for now, we're just going to work on this name, and then we'll look at how to get those other identifiers a little bit later on. So I'm going to jump back over to SQL Server Management Studio. I'm going to go up to File, and I'm going to connect the Object Explorer. And let's connect to Troy-PC. We're going to use SQL Server Authentication because we've just created a SQL Server login. And the login we're going to use is the one we just created. So my login and password of password. Let's connect. And here we are. We now seem to be connected. Now, of course, this is predicated on the assumption that you, as an ethical hacker, can actually connect directly to the database from your network segment. And very often databases are firewalled off in a private network segment. So this doesn't always work, but there are certainly many cases where the database is accessible. So from here, we should actually be able to go and run a new query. So for example, can we get a list of the databases on the server? Yep, there's our databases. There's one down there called Hack Yourself First. So let's see if we can use that database and create some objects. Well, we can certainly use it. Let's try and create something. And we've just created a table. So clearly, we have some rather excessive rights on this. Now, inevitably, what we'd really want to do is say, look at all the tables, identify that there's one called user profile, and then just suck all the data out. And there we go. That's much easier than SQL injection if we can actually get a connection direct to the database. But of course we did that with an initial injection risk. And we found that we had the rights to create a local login. We escalated that privilege to sysadmin. We had the ability to identify the database name. And again, we'll look at how to find the IP address in a moment as well. And then we remotely connected, found the target, and sucked the data out. So that actually got really, really easy. So that's how we can create those database logins. But there's another way we can get remote access as well. And that's if we can discover the password for one of the SQL Server logins. So let's go and have a look at how we can extract that from the SQL Server hashes. One thing to understand about SQL Server is that very often web apps are actually connecting with a SQL login. Now it's usually either that or an Active Directory account, but particularly in web-facing assets, it tends to be a bespoke database account that the web app is using. Now the database has to store these credentials, so somewhere in that SQL Server we have the login stored with both the username and the password. And as you'd expect, the password is cryptographically hashed, but it is stored in the database. And of course that begs the question, how might we get that hash back out? And then how might we crack it as well? Now in SQL Server, and again, this is Microsoft SQL Server, we have a function called pwd compare. And what pwd compare allows us to do is provide a plain text password, and then SQL Server will hash that and compare it to the ones in the database. So let's go and jump over directly into SQL Server Management Studio and see how this works. So firstly, all the logins in the SQL Server can be obtained by running select star from sys logins. So here they all are. And if we give ourselves a little bit more room here, you'll see that we have the name of the login over here in the name column. And if we scroll across a little bit, you'll also see that we have the password. Now for accounts that are actually Windows accounts, so things like this one just here, we don't actually have anything in the password column. This is a Windows login. SQL Server doesn't store the actual password. But in other cases, for local SQL logins, say for the SA account, then yes, the password is stored in the database as a cryptographic hash. Now, what we can do is use that pwd compare function to try and discover which accounts may be using a common password. So let's do this. I'm going to add a where clause to this query, and it's simply going to be where pwd compare, and then the password we'd like to test for, then the name of the password column, which is password, equals 1. So effectively we're looking for where this is true, where there is a password in the password column that is password. Let's run that. And here we have 2 results. And in fact, we can see the one that we just created in the last clip, my login. I've also got another one here that I've used in a previous demo called hacker login. So it's actually found a couple of logins here using that password. Now, of course, we can always run this query remotely through the web app as a SQL injection attack. And if we run this and we discover that there's a login called my login that already has that password, even if we can't create logins ourselves, so for example, the web app is connecting under an account where create login is denied, we still now have enough information to potentially remotely connect to the server. Of course, we've just guessed the word password, and we got it first go because I know that there is an account, in fact 2 accounts, with the password of password. Inevitably though, this would be part of a brute force attack. You'd be enumerating through a dictionary of common passwords, looking for whether it's been used in one of the SQL accounts on the system. So that's a more likely scenario in your ethical hacking activities. So that can be a rather powerful approach. And it's a second way of getting remote access directly through to the database. With that now understood, let's move on and start to look at other ways that we can exfiltrate data from this database and just simply replicate it over to another target database. We've looked at a number of different ways of exfiltrating data throughout this course already. So we've looked at things like a union-based injection, where we pump the data out to the web page, an error-based injection, where we get the data by way of an internal exception, and then of course the blind injection attacks, where we have to actually make assumptions about the data by asking questions. In this module, we've looked at simply connecting direct to the database and pumping that data back out to an external client. Another approach we can use here is the open row set command. And this is something that we can always execute remotely via a SQL injection risk in the web app. Now, open row set is pretty powerful stuff, and I want to show you what it does here. Now, in this case, we're going to use 3 different parameters on the function. The first one is just simply a provider name, and we're using the OLEDB provider for SQL. The second one is the data source. Now this is the data source that we are going to exfiltrate our data to. So this would be your database as an attacker. And you simply need a connection string here that the database you're attacking can use to connect to. So it has to be able to connect out, and your database has to allow it to connect in. Now in this case, my target server is Troy PC. It's my PC, but it could be any machine anywhere on the internet that the server we're running this against can connect to. I'm giving it a target database. So in this case, it's my hacker database, and a username and a password, hacker login, and the word password. The third parameter here is a query against the database that we actually want to export the data to. Now the query is going to be executed by the provider, and it needs to be a query against our database as the attacker, so the one we want to exfiltrate data into. Now I've created a table called city_hacked in my database, the one called hacker database. And what we're going to do is insert into this open row set from the query, which is simply select name from city. So all things going well, if we can remotely execute this command against a vulnerable app, it's going to take all the data out of the city table and transfer it into my database as an attacker into a table called city_hacked. I'm doing it here in SSMS because it's a little bit easier to demo. But let's now run this and see what happens. So we actually have an error. SQL Server blocked access to the statement open row set, or open data source. Now, I wanted to show you what happens here because often open row set is used as an example of a SQL injection attack, but equally often you won't see it explained that by default SQL Server will block this, because from SQL Server 2005 onwards, this is secure by default. You simply cannot run open row set. And when you consider the power of this command, that makes a lot of sense. So this is a good thing to have turned off. So what I'm going to do is turn this back on. And I've got the command on my clipboard. It simply looks like this. We're going to run sp_configure. We want to change ad hoc distributed queries and turn it on. So let's select and then run this statement now. So that should enable it. And now let's select and run the open row set command. And this time it's executed successfully. 5 rows have been affected. So let's now take a new query and we're going to jump over to that Hacker database and have a look inside that table. So let's use Hacker database and let's select star from that table. And here are our results. They've been pumped out into my Hacker database simply by using open row set. But again, I want to reiterate, you cannot do this by default in any modern version of SQL Server. So anything from 2005 onwards. And arguably 2005 is no longer even modern. So when you see this example from SQL injection, it's really only the very, very old versions that it will work on by default. Now, of course, if you have enough privileges on the database, so the web app is connecting with a privileged account, you can always run sp_configure yourself. So as an attacker, you can execute that remotely against the database via an injection risk in the web app, and then you can run the open row set command. So getting around it is not necessarily a very hard thing to do. Let's now move on and take this even further by starting to actually execute commands on the operating system of the database server. So far throughout this course, we've been very focused on running commands against the SQL Server. So getting data out, running system commands, even creating logins so that we can connect remotely. But we can take this a lot further because SQL Server will allow you to run commands on the underlying operating system. So when we can do that, we can go beyond just mere SQL injection and start to actually use that as an attack vector to do other things within the target network. So for example, we could do this. exec xp_command shell. So this is going to allow us to run commands on the underlying system, and then the command we'd like to run. So let's just ping my website and see what happens. And now we see a similar error to what we saw in the last clip, which is simply that XP command shell is blocked by default. And again, in modern versions of SQL Server, this is a secure by default position. This command can start to do really, really nasty things. And much of the time, it's never even needed by the database. So why have it on? Microsoft now keeps it off. But we're going to turn it back on in order to demonstrate this attack, because XP command shell is one example that comes up very frequently when looking at SQL injection attacks. The fortunate reality for those of us defending systems is that it's not going to work on a modern version of SQL Server unless this command has been run. So I'm just going to paste it in from the clipboard, and it's very similar to the one we saw in the last clip. It's just going to reconfigure XP command shell in order to turn it on. So let's now select that and we'll run it. That's now on. Let's go back up and run the XP command shell to ping my website, and now we can see that it's executing the query. And here's the result. So it's just pumped out 1 row per line of result that would normally be pumped out to the command prompt. So in this case, it's actually given us 12 rows of data. So the significance of this is that we've been able to run a command on the operating system itself. And you could easily pass this in via a SQL injection attack too. But of course, we can do much more than just run a ping. Let's actually write to the local file system. So let's pipe this result out into c:\temp ping.txt. Let's see what happens when we do that. Okay, so something has just run successfully. We've got a null output because it's not actually going to return a result from that command, it's actually just writing it to the text file. So how might we get this back out? Well, we're running commands on the underlying operating system. We effectively have a shell. Let's just type it out. So we'll simply change the ping to a type command and run that. And here are our results. And in fact, we could see this execute immediately. I haven't sped it up, so it hasn't executed the ping, rather it's pulled the contents of the file off the local system and pumped it back out to the interface here. This should really start to give you a sense of how powerful these injection attacks can become, because now we're actually pulling files off the local system. I do want to look at this in two ways though. One of them is, yes, it's massively powerful. You can do some serious stuff with this. But the other is, you cannot do it by default. Someone must have compromised the security of their SQL server in order to do this. Now that may be because they legitimately want the SQL server to be able to run operating system commands, but that's probably a pretty bad design decision if it was consciously made for reasons just like this. And of course, even being able to run this, you still have to have both an injection risk in the app and have the app connecting to the database server with an account that has sufficient privileges to run this sort of command. So there are a number of different things that have to line up in order to mount this attack. But it does happen, and you do see XP Command Shell used extensively as examples of just how damaging SQL injection can be. Now there's one more thing I want to look at using this style of attack, and that's SQL injection for network reconnaissance. So let's go and take a look at that now. So we just saw how you could use the XP Command Shell command in a SQL injection attack to run commands on the underlying operating system. Now that starts to open up a world of different opportunities in terms of the damage you can do with an injection attack. Now one of those things that you could do is mounting a SQL injection attack for network reconnaissance. Let me explain what I mean and why that is of value. So imagine that we have you as an ethical hacker. You're going to connect to a vulnerable web app, the one that has the SQL injection risk, and in many cases, that web app is going to connect through a firewall to an internal database somewhere. Ideally, you don't want this database facing the web. Now, the thing about this database being behind the firewall is it's very frequently in a network segment that you do not have direct external access to. But as an attacker, being able to execute commands on a remote machine inside a network segment that you don't have direct access to offers some really powerful reconnaissance options. Because once you're in that environment, you can start traversing around machines that are in that network. So what machines exist? What access do they have? What sources might be on those that are valuable to you as an attacker? Now, in terms of the specific attacks that you might mount when you're interested in network reconnaissance, go and check out Dale Meredith's ethical hacking course on reconnaissance and footprinting. That'll give you a great overview of the sort of things that you want to be looking for when you actually have control of a machine in the target environment. So I hope this gives you an idea of just how far you can take this SQL injection risk. It's about so much more than just reading data that you wouldn't normally have access to, or writing to a few tables. Once you can start executing commands on that remote system, the world opens up in terms of what you, as an ethical hacker, can do to the target environment. This module really started to get very powerful in terms of what we can do with SQL injection. So let's just recap on some of the most important things we covered. And one of the first ones was establishing what sort of rights the account actually has on the target system. Is it just data reader? Data writer? Do we have DBO? So figuring out what you're going to be able to run as an attacker is a very important first step. Of course, the other thing was actually looking at other databases that you can attack. Why limit yourself to just the one the web application is talking to? Particularly when that login account has excessive rights. you may find there's nothing stopping you from accessing all sorts of other, possibly even non-related, databases on the same system. Now, if you can't access those other databases directly, you may just be able to remotely create a new SQL login. If you can remotely create that login and then escalate the privilege into a role such as sysadmin, that could make things significantly easier in terms of the way you traverse around that database. You just remotely connect to it. If, of course, you are actually able to remotely connect from a public network segment. Now, you don't always need to create a SQL login, because remember, you could actually extract it from the hash. So you may well find that you can use that pwd compare function to enumerate through common passwords and see if there are any logins in the database that use it. Once you have that, then there's another attack vector where you may just be able to come into the database directly via that login. Now, regardless of how you get into the system, exfiltration via open row set can be very powerful, and this is a great way of pumping out large volumes of data very quickly. As I said in that clip though, this is not enabled by default in modern versions of SQL Server, and that's a good thing, the secure by default position. So do establish the version of the database server as well, and you'll have a better idea as to whether or not you're going to be able to execute this kind of attack. Of course, that doesn't mean that someone hasn't just manually enabled the feature anyway, and we do obviously often see people configuring systems insecurely like this, but certainly this is one very powerful attack. Another very powerful one, possibly even the most powerful thing you can do as SQL injection, is executing system commands. So once you can run XP command shell, the options open up extensively. And inevitably, as an attacker, you're going to be doing a lot more than just pinging like we did in the example before. Now you're going to have access to all sorts of other resources on the target machine, as well as being able to start doing things like network reconnaissance and looking at the other machines in the environment. Having this command shell is an enormously powerful attack. And as I've said a number of times in this module, it just goes so far beyond merely accessing data in the database server. So this is a really great way to wrap up the topic on advanced SQL injection concepts. And nothing demonstrates the power of SQL injection more than being able to run whatever command you'd like in the target environment.